Let's talk about Newton's method, named after Sir Isaac Newton. First, let's look at a story problem. Suppose we have a car dealer that offers to sell you a car for $18,000 or for payments of $375 a month for 5 years. What you'd like to know is the monthly interest rate the dealer is in effect charging you. Well, we do have a formula that depends on the amount, the payment, and the interest rate. So let's go ahead and put in 18,000 for our amount, 375 for our payment. We're going to put X for the interest rate because that's what we're going to try and find. So then 1 minus 1 plus x to the negative. N is the number of payments you would make. You're paying per month for 5 years, so 12 times 5 would be 60. We could multiply both sides by x over 375, so we could get rid of this fraction, and 18,000 divided by 375 is 48. So we'd have 48x equal 1 minus quantity 1 plus x to the negative 60. Now let's multiply both sides by 1 plus x to the 60, and why we would do that is so we can get rid of that negative exponent. And that will leave us 48x times 1 plus x to the 60 on this side, and if we distribute that through, that'll be 1 plus x to the 60 minus, and this one the exponents would become 0, and I think the 0 here is 1, so this will be a 1. We could take and we could move everything on the same side, and this is what we would have to solve. How are we going to solve this? A lot of times we have things that we can't reasonably algebraically solve, and so we often would maybe look at the graph and see if we could approximate the root. Well, Newton's method is actually going to help us when we can't easily solve, and so we therefore need to approximate the root of an equation. We could first look at a graph. What we're trying to find here is this point right here, and you could kind of zoom in on it to get an estimate. But what we're going to do is learn Newton's method, and what it essentially does then is it helps us to approximate roots when we can't find them algebraically. We have something big and ugly like that car problem. Here's the idea. We want to find this root. We start with some x value, so we're going to start here at x1. And we substitute that in the function, so we go up and we find the function value. So at x1 we have a function value. We find the tangent line to the curve at this point, and we know how to do that because we could find the slope of the tangent line by looking at the derivative there and then use the point slope formula and come up with an equation for this line. We're going to follow the tangent line down to see where it intersects the x-axis, and that's going to be our new approximate for our root, our x sub 2. We're going to repeat that process. We're then going to substitute in that x2 in the function, go up here and find the function value, then find the tangent to the curve at that point, follow it down, and depending on how we're doing here, you can see we would be narrowing in on the root. That's the idea behind Newton's method. This moves a little fast here. I wish I could slow it down, but essentially we're starting here, going up and finding the function, following the tangent to the intercept, going down and finding the function, following the tangent to the intercept, going and finding the function, and you see that as it does that, it narrows in on the roots. Let's look at a couple of applets that'll help us see it maybe just a little bit better. So this first one, we can put in any kind of a starting value we want, so maybe we'll start at 8, and what it's going to do is go up and find the function at 8, and then it's going to draw the tangent at 8, and then it's going to, after it finds the x-intercept for that tangent, substitute that in the function and come up with an approximation for the root. We started at 8 and we ended up at 6.39. Now, if we follow that tangent, I'm going to draw the other tangent, it almost doesn't even show because we've gotten so close to that root. And we could do that a couple times, but we kind of can't even see what's going on here because we're pretty close. And this number is changing if I hit that again, but 6.67698, it's just changing out here because we very quickly narrowed in on the root. Let's try another number. Let's see what happens if we started with 4. Now 4 is over here, and we go down and find the function value. When we draw the tangent, we're going to find the x-intercept for the tangent here, substitute that in the function here, and we're already narrowing in on this root. We could draw a tangent. It didn't hardly show up because it was so close to the function. We're at this value 3.3644, and if I hit it one more time, 3.369, and it is narrowing in, but it's only changing out here now because I am so close to the function. Newton's method converges to this value usually fairly quickly. It's going to depend on where we start, so where we end up. Let's try a 6. And we see that then as we draw the tangent, we've gotten very close already. And so as we look at this approximate, you can see it's changing slightly, but only out here. Now this says an interesting value is 8.8995. So let's go ahead and try that. Notice here we're actually fairly close to this local maximum when we do this, and let's see what happens. When we draw the tangent takes us clear over here to this x-intercept. Then we go up and find the function value. We draw the tangent, takes us down here to this x-intercept. We go down and find the function value. Now we find the tangent line to the curve and follow it over to the x-intercept. I'm going to continue doing that, and interestingly enough, I end up converging very closely to this root I was looking at as I move in here closer and closer now. So I started here and it kind of went crazy for a bit, but you could see the idea behind the concept. It ended up converging to this root. So let's see how we would use this. If we wanted to find the square root of 2, the first thing we're going to do is write down an equation whose solution is the square root of 2. Let's do f of x equal x squared minus 2 equals 0. You can see if you solve this equation, if you move the 2 over and you square rooted both sides, you'd have plus or minus square root of 2, but we'll solve this for the positive root. Well, you could graph this. This is a parabola that is vertically shifted down to, and in fact there are two roots, and one would be the positive square root and one would be the negative of the square root of 2. So we can see those on here. So we're going to be approximating this value using Newton's method. We're going to start with x equal 1. We're going to pick something kind of near this root to start, but we'll get in a little closer so that we can see what's going on. So let's go find the function when x equals 1. Starting right here at x equal 1, we go down and find the function, and the function value there is negative 1. That's just simply putting a 1 in the function. 1 squared is 1 minus 2 is negative 1. So we know the function value here. Now can we find the tangent to the curve here? And we can. We want to find the equation of this tangent line. Well, the first thing I would do would be find the derivative so that we would have the slope that we need, and the derivative is going to be 2x. So for this particular line that we have, we need the derivative when x equal 1, so that is 2. So our slope is 2. So we'd have y minus the y from the point, which is negative 1, equals the slope, which is 2 when we put a 1 in here, times x minus the x from the point. So this is y plus 1 equals 2x minus 2. So we just found the equation of the tangent to the curve at this point. Well, what we now want to do is follow this tangent down until we find this point of intersection. How do I find the place where this crosses the x-axis? Well, it's where the y value equals 0. So I could solve this and have 2x equal 3, x equals 3/2. So our new value here, our x2, which is the x-intercept of this tangent, is going to be 3/2 or 1.5. Now we're going to repeat this process then. So we're going to zoom in a little more so that we can do that. And I'm going to go ahead and get this other stuff off the screen. Okay, so we now have this point right here was 1.5. And we can use that and plug that in the function. 1.5 squared is 2.25 minus 2 is 0.25. So we can find the function value there. We now want to find the tangent to the curve there. And so we zoomed in a little more so we could see it, because the tangent to the curve there is getting very close to the function. Can we find that equation for the tangent to the curve? We can. It's going to be y minus the y from the point, which was 0.25, equals the slope when the x is 1.25. Well, here's our slope formula. So 1.25 times 2 is 3, times x minus the x from the point, and that was 1.5. So remember, our point was 1.5 and 0.25. And now we could solve this for y. We've got y equal 3x minus 4.5 plus 0.25 5. We could combine those and have y equals 3x minus 4.25. Now, if we want to follow this down to its x-intercept, we want to find out where this equals 0. So 3x equals 4.25, and x is going to be 4.25 divided by 3. So that is 1.41667. So our third approximate for this root is 1.41667. So we've done this procedure twice, and that's what we got. Well, let's put the square root of 2 in a calculator, and this is what we get for the answer. So we were accurate to 2 decimal places by doing 2 of these applications of Newton's method.